All right, let's talk about one of the absolute toughest challenges in electrification. I'm talking about the cement mixer. Think about it. It's incredibly heavy, its power needs are just nonstop, and its main job, mixing that concrete, well, it absolutely cannot fail. So the big question is, how in the world do you build a high-voltage hybrid system for something this demanding?
Well, that's exactly what we're going to break down today. This explainer is basically a complete engineering blueprint, and it's all based on a really detailed technical white paper. We're not just talking about bolting a few parts together here. No, we're going to dive deep into a true systems engineering approach, the kind that bakes in power, safety, and rock-solid reliability right from the very start.
And here's how we're going to do it. We're taking what you might call an answer-first approach. Everything we're about to cover is built around 5 core pillars. These are powertrain topology, system architecture, the core application, safety and communication, and wrapping it all up, the development process. Think of this as our roadmap to success.
Okay, let's jump right in with pillar number 1, powertrain topology. Now, for a truck this specialized, picking the right architecture, it's not about what you'd like to use. There's really only one correct engineering answer. And that answer is the P2 hybrid architecture. That's where you put the electric motor right between the engine and the transmission. And look, it's pretty much non-negotiable for a few key reasons. First, it gives you that massive torque you need to get a fully loaded truck up a steep hill. Second, it lets you operate silently in all-electric mode on a job site, super important in sensitive areas. And third, it's just brilliant at recapturing braking energy because it uses the truck's own gearbox. But wait, there's another layer to this. So even within the P2 setup, you have another critical choice to make. You see, a standard coaxial motor actually makes the whole powertrain longer. And on a chassis where every inch counts, that's a total deal breaker. So the mandatory choice here? It's the off-axis design. This is what keeps everything compact, it kills nasty driveline vibrations, and it even makes future upgrades way easier. So, we've got the mechanical layout sorted. Now it's time to build the electrical heart of this beast. That brings us to pillar 2, system architecture. This is where we get into the really foundational stuff, the decisions on voltage, how power gets distributed, and which components make the cut.
Now, you hear a lot about 800-volt systems, right? They're getting all the hype in passenger cars. But for a heavy-duty commercial truck like this one, you know what? 400 volts is actually the smarter engineering call. Why? Well, for one, the supply chain is way more mature and it's cheaper. It also works with the industrial chargers that are already out there. And maybe most importantly, it gives you a much better safety margin in the dirty, dusty, and sometimes damp world of a construction site.
So, the whole electrical system is built on 3 core, non-negotiable principles. First, you have one single energy source, one main battery. That just makes managing everything so much simpler. Second, everything flows through a centralized power distribution unit, the PDU. Think of it as the system's main circuit breaker panel, offering focus protection. And third, you physically separate the circuits that charge up the system from the ones that discharge it. That way you get rid of any single points of failure. It's all about building in toughness from the very beginning. And that focus on being robust, it goes all the way down to the individual components. You know, choosing what goes inside isn't just a matter of preference, it's straight-up physics. For instance, inside that PDU, you absolutely have to use a laminated bus bar instead of just stringing cables together. It's the only way to stop voltage spikes that would literally fry the electronics. Same goes for the inverter. You've got to use film capacitors. They can actually self-heal, they have lower resistance, and they're just built to survive the brutal electrical environment inside a hybrid system. Okay, so now we get to what is arguably the single most critical part of this whole truck. I'm not talking about driving. I'm talking about the system that powers the mixing drum itself. This is the electric power takeoff, or the ePTO.
But before we dig into the solution, I want you to really think about something for a second. What is the absolute #1 most catastrophic thing that can happen to a cement mixer while it's out on a job?
It's what's known as a set load, and it's exactly what it sounds like. If that drum stops turning for any reason, all that concrete inside starts to harden. It turns into one giant, useless block of stone. We're talking about a failure so bad that sometimes they have to scrap the entire truck. So, whatever we design, the electrical system must prevent this from happening. No excuses.
So, how do you guarantee that? Well, the only way is with a multi-layered defense strategy. This isn't just a nice to have. In our blueprint, this triple redundancy approach is absolutely mandatory.
And here's what those 3 lines of defense look like. First up is smart, fail-safe logic. If a small electrical fault pops up, the system doesn't just shut down. No, it goes into a limp home mode to keep that drum turning. The second line of defense is a good old-fashioned mechanical backup from the engine's PTO. And for the absolute worst-case scenario, a total vehicle failure, there's a third line, an external hydraulic port. This lets a rescue unit, to call it a drum saver, literally plug in and take over, keeping that concrete from setting.
All right, let's move on to the truck's backbone and its nervous system. This is Pillar 4, safety and communication. It's all about the protocols that make sure every single part of this system works together safely and reliably. And here's a perfect example of a critical safety detail. We're talking about the high-voltage interlock loop, or HVIL. That's basically the safety circuit that makes sure all the high-voltage cables are securely connected. Now, you might think you could just check this with a simple DC signal, but that's actually forbidden. The mandatory way to do it is with a pulse-width modulated, or PWM signal. Why? Because it's so much smarter. It can tell the difference between a cable that's just unplugged, one that's shorted to the truck's frame, or one that's shorted to another power line. The diagnostics are just worlds better. And when something does go wrong, the system has to react fast. I mean, from the instant it detects a break in that safety loop to the moment the high voltage is totally shut off, the whole thing has to happen in under 100 milliseconds. That's incredibly quick. Now, to prevent electric shock, something called equal potential bonding is absolutely critical. What that means is that every single metal part of the high-voltage system is securely connected to the truck's main frame to ground it. And the connection has to be nearly perfect. The rule is that the resistance between any two of those connected parts has to be less than 0.1 ohms. That's a tiny, tiny number. And if we're talking about the truck's nervous system, we're talking about the CAN bus network. This is how all the computers talk to each other. To make sure that the really important messages, like a command for more torque, are never delayed or lost in the traffic, you have to manage that network very carefully. The rule of thumb is to never let the average bus load, or network traffic, get above 60%. That leaves plenty of room to guarantee real-time performance when you need it most.
So that brings us to the final piece of the puzzle. How do you take all these rules and requirements and make sure the whole complex system gets developed correctly? Well, that's our fifth and final pillar. A disciplined, structured development process.
And the key to that is following what's known as the V model. It's a super clear and rigorous way to do things. Think of it like this. On the left side of the V, you go down, defining all your requirements, starting with the whole vehicle and getting more and more detailed, all the way down to the tiniest component. Then you come up the right side of the V, testing and validating at every single one of those levels. It's a system that makes sure absolutely nothing gets missed.
And really, this gets to the absolute core of it all. Being successful in vehicle electrification isn't about just going out and buying the fanciest components off a shelf. No way. It's about mastering a systems engineering approach, where the process you follow is so good that it practically guarantees a successful outcome.
So, what's the real value of a blueprint like this? Well, it hits three huge goals. First, it helps teams that are used to thinking in terms of diesel engines make the leap to electrical systems engineering much, much faster. Second, it stops you from making those huge, expensive mistakes in the beginning that force you to start all over again. And third, it builds a solid foundation that you can use later for all-electric trucks or even ones powered by fuel cells.
And at the end of the day, that's the real takeaway here. It's all about a fundamental shift in thinking. By embracing a structured, systems-level approach like this one, engineering teams can really move beyond just what they know from the past. They can start building the foundation for the next decade of truly amazing innovation in commercial vehicle tech.